Hi everyone, today I'm going to be using GeoGebra to look at some gradient functions. So this is what we did in class. I'm just going to start a new calculator here in a browser window and let's have a go. So first we need a function of x. We'll just go with a straightforward polynomial, something like this. There we go. So it's a lovely little cubic function. And what are we looking at here? Well, we've got a 0 at 0 and at -1 and at +2, so that's good. We've also got turning points in between those as well. More about them in a minute. Now, in order to start exploring this, I want to have a point which I'll call A, and this point will be attached to the function. So there it is. I can drag that along, and I can't take it left or right. It's locked onto, so it'll slide around. I can even hit the animate key if I want to, and it will move by itself. That's good. Now, when I'm talking about the gradient of a curve like this, we define that, remember, to be the gradient of the tangent line at any particular point. So I need a tangent line to this curve at point A. You guessed it, the command is tangent. I need to tell it the point of interest, point A, and I also need to tell it the function that we're working with, f. So I've got my tangent there. As point A moves around, obviously the tangent changes because this is a curve. The gradient is changing for a curve. Straight lines have a constant gradient. Curves, the gradient changes. Otherwise they wouldn't be a curve, would they? So the thing that I'm most interested in about this tangent, so the tangent's lovely, but the thing that really interests me is the number here, the gradient of the tangent. I don't care about the y-intercept. That's the bit that I'm really interested in. So I will use a variable m. M is a traditional letter we use for the gradient of things. The GeoGebra command for this one is slope, and it's the slope of the tangent. The tangent is labelled g, so it's the slope of g. Now, that draws a lovely little triangle in here with a base of 1 and a height, obviously equal to whatever the current gradient is. That's nice. As I move point A, you can see the gradient is increasing quite a bit. As I come back this way towards the minimum, you probably wouldn't be surprised to find that the gradient, I can't quite get onto that exact spot, that's close enough I think, that the gradient there is 0. I'm not quite exactly on the minimum point, am I? Then gradient negative, gradient 0, and gradient positive, and it changes all the time. Now, what I would really like to do, I might just turn off that little triangle. What I would really like to do, I'm just going to resize that slightly by stretching the x-axis a bit so it's easier to see, is I would like to be able to keep track of the gradient value. So I'll define a point capital G. I want this to move in sync with point A, so it will share the same x coordinate of point A, and its y value will be the gradient. So there's point G, and as point A moves, the tangent changes, the gradient is getting lower, so point G is coming closer, coming down a bit. The turning point, right about there, the tangent is horizontal with a gradient of 0, and point G has a y coordinate almost 0. If I were to just animate that, focus on point G. It'll come back in a moment. Point G is, there it is, it's coming down, it turns, and then it goes back up. It would be lovely, sort of stop that a bit too soon, I want point G visible. It would be lovely to actually see what point G is up to. So if I just clicked on point G and then there's a little menu here, I can show a trace. Point G will leave a trail behind as it moves now. So that series of black dots represents the places where point G can be. So point G is tracing out the gradient function. the gradient function is also called the derivative of f. Now, that's lovely. The trace function is a little bit nasty. I'll show you what I mean. If I was to zoom in or out, GeoGebra erases all the traces for good reason, otherwise it would get very messy. I'm going to turn the trace function off. I'll show you another way to get GeoGebra to draw this. There's two different ways actually. I can use the command locus. Locus is a bit of an old-fashioned geometric term that means the location where point G could be found. Point G is the one I'm interested in. I want to know all the locations that point G could be found. Now GeoGebra needs me to tell the computer point A as well, because point A is dynamically linked. It's controlling where point G's behaviour is. So that gives me the derivative function right there. I can just draw that in. Away we go. Isn't that nice? And here we go again. So that's one way to find the derivative function using this locus command. I'll show you another way as well. I'll take that one away. My original function f of x, which I just typed in as a polynomial, a cubic polynomial, GeoGebra is clever enough to understand the notation f dashed x. I'm sure you've learned in class f dashed is an abbreviation for the derivative or the gradient function of f. So there it is. And it even tells me the polynomial form of this thing. And there you go. As point A moves along the cubic function, I've got the tangent line drawn there, and then point G is sliding around the derivative function. I don't even really need the tangent line to be there. The tangent line is just an idea, but point A can move along the green function, the original one, f, and point G, which represents the gradient at the location of point A, it slides along that blue function, or f dashed of x. In fact, I don't even really need the points. And this is the thing. When you start getting a bit more accustomed to calculus, you will start talking about the derivative of a function, and you won't even think about what's behind it. What's behind it is what we've presented here in this little video lesson. What's behind it is a point moving along the original function, and we're thinking about the gradient of the tangent at that point. And then more importantly, we're tracking the gradient of the tangent as it behaves, and it traces out a different function. Now, you will probably start to see past the points and the tangents and things. You'll start to think of derivatives just what's presented on the screen there at the moment. So the original function was a cubic, that's the green one. The derivative is a quadratic, that's the blue one. There it is. But never lose sight of the fact, and come back and remind yourself of this at times too, never lose sight of the fact that a derivative is a function that tracks how the gradient changes. The gradient of f is changing, the derivative is the function that tracks how that changes. Because that's really the key idea that you need to embed in your mind when you think about derivatives. The other thing that this is useful for, apart from learning, is that we can change this. We could change this, and it should update. Now let's make it x cubed minus 3x squared plus, or in the wrong place there. Oh, I hope I don't wrong this. Plus 2x minus 1. I have a new cubic. Everything has updated, and importantly, my derivative has updated as well. So this whole GeoGebra worksheet will keep doing what you want it to do. If you just change the original function, everything else is linked back to it. We could even move away from polynomials. We could start doing more interesting functions like let's go 2 to the power of x. We studied exponential functions a little while ago. Now, 2 to the power of x, here we go. That's cute, isn't it? The green one is 2 to the power of x, the blue one is the gradient function. It seems like it's almost the same, it's just a little bit lower. I wonder what would happen if I made that 3 to the power of x. Well, now the blue one is a little higher. The green one, remember, is the original function. The blue one is a bit higher. That immediately makes me think of a challenge. I wonder if I could pick a number as the base here where they were the same. So now the blue one's a bit lower. 3 was too high, 2.5 is too low. Well, I'm going to go for 2.75. And they're almost the same. Look at that. The original function, f of x, 2.75 to the power of x, is almost, it doesn't look the same there, but we can see that its behaviour is almost the same if I have that. Now, of course, those of you who've studied a bit more calculus than I'm presenting here will realise they're not exactly the same. Look at that. I could keep playing around with these numbers a lot. Like I could randomly select 2.182818, I think. Oh, look how close they are. So, yes, that wasn't random, of course. Anybody who knows this will recognise that's one of our special numbers in mathematics called E. So it turns out, if I just zoom back a little here, it turns out, oh, I've gone wrong, hit the home button. It turns out that if I have this function e to the power of x, the derivative is the same. Anyway, I've spoken for too long. That's enough for now. Give it a try yourself and enjoy. Thanks for watching.